Okay, hello class. So chapter 1, we're going to learn about problem solving with mathematical models. So this is mostly of some vocabulary for us, and then connecting it some ideas we've had in other classes, other math classes. Okay, so I just want to start off with an example that you've probably seen in a calculus class. Find two positive numbers. We'll eventually consider if they're integers, but usually the problem in that class is presented. Find two positive numbers whose sum is 23 and whose product is as large as possible. So what we're trying to do is maximize something. And this is a function of two variables, x1 and x2. Those are called our decision variables in this class. We use that language a lot. They're going to be the things we're trying to decide on. What are those numbers? We want to multiply them. That's our objective. Actually, it's an objective function. Okay, and we could also write it as f of x1, x2 is equal to x1 times x2. These are a set of constraint equations or inequalities. So again, some language you probably had from calculus. And what we're trying to do here is make sure we can't make them as big as possible. You can't say like a million times a million because you have this extra information, this constraint that they have to sum to 23. Usually you didn't think about these constraints. These are often called simple constraints because they're in this form. They're usually just very short statements, not linear functions, just, well, there are linear inequalities, half spaces, that x1 is greater than 0, x2 is greater than 0. So that's the part where it's positive. And again, in calculus, introductory calculus classes, you usually kind of ignore these simple constraints. And then we might also add that they are integers. So here's the first part of the problem, and then we're going to add two more simple constraints saying that they're actually have to be integers as well. Okay, now definitions of a couple terms here: feasible solution and optimal solution. So a solution is just something that satisfies your constraints. So example, if you set x1 to 2 and x2 to 21, yes, that satisfies this one. Yes, they're both positive. Yes, they're integer if you're doing that version. Other examples for the part where it's just doing the positive ones, you could use any decimal. X equals 2.5, x2 equals 20.5. Okay, and so because if you're opening up decimals, infinitely many feasible solutions. If you add the integer simple constraints, there's a finite number, but it's still a large number of solutions, feasible solutions. Just to maybe show the graphically, because we are going to do a good bit graphically with this one, these two here. Right, that's just x1, x2. Right, that'd be the whole non-negative region here, x1, x2 greater than 0. If you're adding the fact that they're integer, so all four of these simple constraints now, it actually looks like this. It's the grid or the lattice, where these are integer values. 1, 2, 3, 1, 2, 3. Then we only have these. Oh, we're greater than or equal to 0, so we actually have x's as well. All right, so a finite number of these discrete solutions, they're called. So this is often when you add the integers, it becomes something called discrete optimization. And this would go on, except we actually can add one more constraint. x1, x2 equals 23. So in this picture, if this is 23, this is 23 along the axis. We're actually the feasible region now for the first three constraints. And another color, let's see if the screen works. If we wanted this set of constraints, we are now just along this line. Only the part in the non-negative region along that line. Then the same thing would happen here. We'd have to go all the way up to 23. That breaks the graph. Here's 23. Here's 23. And so it would only be any of the dots that would lie along that line. So there would be a set of dots on this lattice. That would be the feasible region of all 5. Okay, now the optimal solution next term has to be feasible, right? You have to satisfy your constraints, and then you want to maximize or minimize if that's your objective. Ours here is maximize. So we want to find the one with the largest objective value. Oh, sorry. So for this one, this is not, that's a feasible one. An optimal one would be what? We multiply these two things, 11 and 12. But that's not the only one. What's another one? Just flipping those. X1 equals 12, X2 equals 11. That was when we had the integer part. What if we were doing just the first 3 constraints in green? Then you would be solving this, and maybe here's a good time to pause the video and think about how would you solve this with calculus. So we'll talk about that in a moment. Okay, so back to our problem in calculus, you would have really ignored the part about positive numbers or integers, and you would have just set up this function. I want to maximize the product. So I have a function of 2 variables, x1, x2, subject to this constraint. And usually what you did is you made a solved constraint over here. So solve for one in terms of the other, push that back into the objective. This is a function of 2 variables. You were good at handling functions of 1 variable. So you pushed it into the objective, formed this function of just x1. It's x1 times 23 minus x1. Simplify. Then you took a derivative to get a critical point. Those were good places to look for extreme values, extrema. And you solved that this was the critical point at 11.5. You could do the second derivative test or the first derivative test and determine that that critical point actually is a max because the function was concave down. To get the x2, then you used your solved equation and you found, and this is just some notation for us. In this book and most optimization books, we like to write x star is actually a vector of 2 components, x1 star. The star is telling us that that is notation, that it's optimal, and it's at the values 11.5, 11.5. Okay, so it turns out that then you check, okay, it is positive. Now, if they had extended it to the integer version, this doesn't work. And so we have to do other techniques. Again, we have to actually add those simple constraints, x1 is x2 is integer, and we can't use the calculus method to do this. Okay. Okay, a few more vocabulary terms from this chapter. So we just dealt with that with calculus, and so we ignored the integer ones. And when you do that, you've done something that's called relaxing the optimization problem. So we actually solved the relaxed optimization problem. If those integer values were in there, we don't have a method to do that. We're gonna have to do something else, and we will get to that. We'll learn that whole field called discrete optimization. Another thing we often do with optimization models is we conduct a sensitivity analysis, and we're wondering what happens when certain parameters change. So for instance, what if, this is modeling a particular situation, you have a client and they come back and say, well, we're not so sure that's 23, maybe it's 25. Well, in our previous method, the solution of, we identified calculus, that would have changed. That value would have no longer been optimal. Now, they might also add a constraint like, well, not just greater than 0, maybe x1 has to be greater than 1. Well, that optimal solution that we had gotten by calculus, the 11.5, 11.5, that would have maintained, still would have been an optimal solution. And we just sort of did a guess and check and logic approach to find for the full problem with the integer values that 11, x1 equals 11, x2 equals 12, or vice versa, was the optimal solution. And that would no longer be feasible if we added this constraint, change this parameter, and it still would be with this one. So this one doesn't affect us. And that often happens. Sometimes you're modeling a problem and you have some constraints in there, but you then find out that it is redundant. It is subsumed by other another constraint or other sets of constraints combined to actually make that not a restrictive constraint for you. Okay, a couple other terms, tractability and validity. So we're often going to talk about the tractability of a model or the validity of a model, and they mean what they sound like. So, and there's going to be this constant trade-off. You want to make a model that is valid, that's accurate, it correctly captures what you're trying to model, the situation that your client came to you with. But there's always this trade-off, because in doing it, the most accurate model, sometimes that makes it impossible to solve, or very difficult to solve, or it takes a very long time, or the computational expenses are more than your client wants to bear. And so that is the tractability. Tractability has to do with the ability and ease with which you can implement it and actually find a solution. Another idea here, another term is, we'll use this often in class, total enumeration or brute force. If you wanted to solve a problem, so let's say again, we add our integer constraints, we're looking on the full problem, can't use calculus then, we use some logic to kind of think about it, had to be 11 times 12, you know, that multiplies in a much bigger number than say 2 times 21, that's only 42, 11 times 12, okay, that's much bigger, we're getting closer to logically think that that was the optimal. And really what we were doing there is a smarter type of total enumeration, right? In total enumeration, you might make this list where you're like, here's values I'm going to plug in for x1, for x2, and then I'm going to see what the objective function, x1 times x2, is. And you're making 3 columns. And you're just trying values that satisfy this, that they have to be integer. Maybe you start with 0, 0, then you go 0, 1. But wait, that's not a constraint. So then we're like this, 0, 23, 1, 22. And you're going to systematically list and see what happens. 0, 22, 2, 21, 42. And you're just going to keep on going until you've covered all possible values of doing that. So you're really traversing that entire lattice that we had talked about in a total enumeration method. And this is a very useful technique for very big problems. Obviously, if I have, I'm not just going up to 23 or I have many more variables, this is computationally expensive, but often it gives you a handle on the problem. And it's a good first step to get some, shed some light on something that might work smarter in the future. So this is a useful thing, total enumeration, or sometimes we'll call it brute force. Okay, next pair of terms is exact versus heuristic. So a heuristic is going to give you an approximate solution. That is a, sometimes you know you can't get an exact thing, it's just too expensive. You can't prove that it's exact. All you can prove is that you've created an algorithm that is a heuristic algorithm. It's going to do the best it can and come up with an approximate solution. That's a very good solution. Sometimes you can go a little bit further and say, I know that this heuristic is epsilon optimal. Often that means you're within some epsilon of the optimal value. You don't actually know what the optimal value is, but I know I'm within 5%. There's certain special cases for certain problems where you can come up with those guarantees. So epsilon optimal is the phrase you're here. The next pair is deterministic versus stochastic. This class covers deterministic models, but also know that stochastic models exist. Stochastic models are simply where some of the parameters, like maybe the coefficient is an invisible 1 in front of this, invisible 1, maybe this, or this, maybe one of those coefficients there, the 23 or the coefficients are only known with some probability. So again, we're not certain about 23, maybe it was 25. Or maybe we know there's some range in there. We're 90% sure this is 23. That generates a stochastic model. That's a whole other field called stochastic programming. But we're going to stick with deterministic in this book. Okay, last thing is there's some suggested homework problems. Again, your quizzes will come directly from these. You have time to work them at home at your leisure. And then on the quiz, you'll have a time quiz chosen, selected from your selected homework problems. Okay, so this is chapter 1. We're looking at numbers 3, 5, 6, and 8. All right, lots of vocabulary in chapter 1, and then we're going to get to some problem solving in chapter 2.